Welcome to another lecture on unique and interesting quantum mechanical topics. This week's topic is dispersion, which is a consequence of superposition of multiple waves in a medium where the wave components don't propagate at the same speed. A complex wave function is written with two exponentials. I might write one being complex and the other being a decaying exponential. And you might break apart that exponential. Let's do that so that we can talk about these different factors for a minute. You have the complex term that has an omega t, a kx, and a phase offset. Let's define each of these things. An amplitude, it won't be very important to us for understanding dispersion. This e to the minus beta x is for attenuation. It also won't be very important to us. We're not going to continue having it. It's a decaying exponential. It's the rest of it that matters. E to the I omega t describes the oscillation in time of a wave. E to the minus ikx describes the propagation of the wave. E to the minus phi 0 has no variable in it. Should be the simplest thing, but it's often the most conceptually difficult to grasp. It's the phase offset. If you made a graph of a cosine wave, you can describe this as a cosine, but it doesn't have its peak at 0, and so this offset between where the peak is and where 0 is has to be added in, and this is how it gets included in as something called the phase offset. It's just a constant. We'll be focused entirely on these two terms, oscillation and propagation. Let's go ahead and put it back together. Look at the first line here again. This argument of the complex exponential, omega t minus kx minus phi 0, is the phase of that wave function, just as much as e to the minus beta x is the decay of that wave function. Phase has both position and time dependence in it, and it describes the sinusoidal structure down here. I'm going to choose a random point on this wave, and I'm going to stay with it. As time and x change, I'm going to stick with that spot right there. So I'm basically going to fix myself here and move with the wave as it moves. I'm going at a certain speed now. What speed am I moving at? I'm moving at the speed of a point of constant phase in the wave. So let's find how fast a point of constant phase propagates. That is, let's find the velocity of a phase point, the phase velocity of the wave. Taking that argument of the complex exponential, omega t minus kx minus phi 0, if I ask how fast is a point where phi of xt is constant moving, take the derivative of phi of xt and set it equal to 0. Now you are describing a point of constant phase on that wave. That point has a certain position and a certain t, a displacement over time. And so if you take that derivative, recognizing that x is time dependent, you have dx by dt in here. You have the displacement of a point of constant phase with time. Dx by dt then is omega over k. It's the phase velocity. So phase velocity is omega divided by k. That's the conclusion here. The speed of a point of constant phase is omega divided by k. If I take out the 2 pi's, I'll get something that's a little more familiar to me. Changing omega to 2 pi f, k to 2 pi over lambda, I find that the phase velocity is lambda f, that familiar expression. The meters per second is meters per second. Remember, we had this expression in general physics that the speed of light is the wavelength times the frequency. Evidently, the speed of light is the phase velocity of light. C is the phase velocity of light in vacuum, 2.998 times 10 to the 8 meters per second. Another important conclusion is that when you have a sinusoidal function, omega t minus kx, with or without a phase, the ratio of whatever multiplies the time divided by whatever multiplies the position is the velocity of that sinusoidal function. The velocity of a sinusoid is whatever multiplies the time divided by whatever multiplies the position. And there's a sign issue here too. You notice this is omega t minus kx the way I wrote it, this plane wave. I could have written omega t plus kx. What would be the difference? If it's omega t minus kx, then the velocity is plus omega over k. If it's omega t plus kx, then the velocity is minus omega over k. going in the opposite direction. So omega t plus kx would be a wave that's moving in the negative x direction. When you put two waves on top of each other with slightly different either wavelength or frequency, so I have sine of kx superposed on sine of 1.1 kx. They're both graphed together. Clearly, if you go out far enough, you'll actually get to a point where they're canceling. At 1.5, they're pretty much constructively interfering, but eventually they're going to destructively interfere. Let's go ahead and plot these two together, added together, one plus the other, for a long number of periods, and we do find the beats. There are points where they destructively interfere, points where they constructively interfere. Otherwise, you seem to have a single oscillation, a single sinusoid, that's modulated by a very long wavelength sinusoid. That's the modulation envelope. The sine of kx and sine of 1.1 kx certainly are almost the same on this graph. When you add them together, you get the points of destructive interference. Let's focus in on just one of these modulation envelopes. I see I have a high frequency oscillation or short wavelength oscillation, and I have a low frequency oscillation or a long wavelength oscillation. If I pick a point of constant phase on the fast modulation and ask how fast is it going, I might not get the same answer if I picked a point of constant phase on the modulation envelope and asked how fast it's going. So let's assume they're different for now. The phase velocity is the point of constant phase on the high frequency oscillation, but the modulation envelope can also propagate. We'll call it the group velocity because it describes a group of waves superposed together. And this modulation envelope then moves with the group velocity. They're not the same in general. Here's an example of the phase velocity being much larger than the group velocity. So the red box is a point of constant phase. It's moving at the phase velocity. You notice the green dots are always at the same place in the group. They're all positioned right where the destructive interference happens. They're moving a lot slower. It doesn't have to be that way. Here's a case where the group velocity is faster. The vertical line is following the wave packet. If you look at it, it keeps going past points of constant phase. They're going forward too, but much slower. And it can get weirder. You can have them going in opposite directions. So in this case, the group velocity is going to the right, but the phase velocity is going to the left. Just follow a point of constant phase, and you realize you're heading to the left. We can get an expression for the group velocity, just like we got an expression for the phase velocity. So let's take our two waves. One at frequency we'll say omega 0 plus d omega, and the other is at frequency omega 0 minus d omega. We could call them anything we want, but I'm going to call them that. So omega 0 is just halfway between the two frequencies. And since omega is phase velocity times k, it would follow that there's also a wave number, k0 minus dk for the first wave, and k0 plus dk for the second wave. Put these omegas and these k's into the expression for psi. You have one wave function for each one of them. You're going to have to add two exponentials together. And you notice I didn't put an amplitude in front, so we're really just concerned about what happens inside the argument. And I'll just keep it that way to not obscure things. And you have this combination. You have your omega 0 minus d omega and your k0 minus dk and then plus over there. Rearrange these exponentials slightly to get the differentials to group together and the non-differentials grouped together. Take a minute and look and realize these are the same expression, just rearranged slightly. But now I realize that these two terms have a common factor of e to the I omega 0 t minus k0x, which I can factor out. So pull out that common factor, and in square parentheses then I have what's left, exponential with the differentials in the argument, e to the minus I d omega t minus dkx. You might recognize this as a cosine. It's actually 2 times cosine of that argument. Again, I have no amplitude, so I won't worry about the 2. But you can replace what's in the square brackets with 2 times cosine of the argument. Go ahead and do that, but like I say, don't worry about the 2 because we're not dealing with amplitude. And I have this rearranged expression for the wave function of two waves superposed with maybe very similar frequency. So d omega is much less than omega 0. And so very similar wavelength, so dk is much less than k0. That makes an important point, then, that this factor e to the I omega 0 t minus k0 x is a high frequency oscillation. And this cosine is a low frequency oscillation. So the high frequency oscillation in signals is usually called the carrier. It travels at what multiplies the t divided by what multiplies the x, omega 0 over k0. As opposed to the modulation envelope, which travels at a different velocity. And now we're ready to write down what that is. Because you have these two traveling waves, the phase, or the carrier, and the group, or the modulation. The modulation argument of that cosine is d omega t minus dkx. If you just set equal to 0, you have a point of constant phase, and how fast is it going? You just rearrange it. X over t, displacement over time, is the speed of that cosine. The group velocity then is d omega divided by dk, which we'll just call d omega by dk. That's the important expression. You want to write that one down. The group velocity is d omega by dk compared to phase velocity, which is just omega over k. Here's an interesting question related to quantum mechanics. Consider a free particle. Does it move at its group velocity or at its phase velocity? Well, a free particle is described by a Gaussian wave packet. And so here's a simulation of a Gaussian wave packet moving along. The free particle is wherever that wave packet is. So if the wave packet moves, the free particle goes with it. The velocity of the wave packet is the velocity of the envelope. The group velocity apparently must be the velocity of a free particle. The phase velocity is noticeably different. Just watch as it goes by. These points of constant phase are not keeping up with the group. We can work this out by looking at the energy of a free particle, p squared over 2m, where momentum is h bar k. This is the quantum mechanical momentum. But also, Planck's hypothesis, energy of a wave is h bar times omega. Those two are the same, so equate them. You can cancel out an h bar when you equate them. If I want to know the phase velocity, I should find omega over k, so I do. Phase velocity is h bar k over 2m. If I want to find the group velocity, I should differentiate omega with k. So d omega by dk, differentiating this expression, is h bar k over m. Evidently, the phase velocity is half the group velocity. The group velocity is twice the phase velocity. And that was actually done in this simulation. If you look closely, you see the group is going at this speed. A point of constant phase is going at exactly half that speed. That was deliberate in the simulation. And since group velocity is p over m, right, it's h bar k over 2m, the group velocity is going at what we would in classical mechanics call the velocity, momentum divided by mass. It is the velocity of the wave. Since group velocity is d omega by dk and phase velocity is omega over k, it would follow that group velocity and phase velocity certainly have something to do with each other. Let's find what that something is. That relationship between group and phase velocity is going to define dispersion regimes. Start with the expression for group velocity is d omega by dk, but k is related to phase velocity. So replace k with omega over v phase in that derivative. And what we're really doing then is we're going 1 divided by the d by d omega of omega over phase. Do you follow that argument? Make sure you do. And take that derivative, d by d omega of omega, and then you have to go d by d omega of 1 over v phase. And so that's the derivative after you've applied the product rule. I can always multiply things by 1, so go ahead and multiply by 1 just to clean this up a little bit. And you have a simplified expression where v group is v phase divided by 1 minus something. That something being omega over v phase times the derivative. We can furthermore simplify it by replacing omega over v phase with k. That's a common expression now for how group and phase velocities are related. They're related by this derivative. If this derivative didn't exist, if it had zero value, then group velocity would be phase velocity. You would say that is a dispersion-free system. Dispersion is the fact that group and phase velocities are not equal. A slightly more sophisticated way of putting it would be that phase velocity depends on frequency. I've said nothing yet that suggests that that derivative has a particular sign, plus or minus. I just mentioned maybe it's zero in some cases. I want to examine this expression with the question of what are the consequences of the different signs for that derivative. Beginning with negative. So if this derivative in the denominator, dv phase by d omega, is less than 0, it would follow that the denominator is greater than 1. The group velocity is less than the phase velocity. That's normal dispersion. In electromagnetism, when a wave propagates through a dielectric medium, that's usually the case. The group velocity will be less than the phase velocity. Except in that situation where the dv phase by d omega is positive. Because if that's positive, then the denominator is less than 1. The group velocity is less than the phase velocity. That's called anomalous dispersion. It happens in a case when you have atomic resonant absorption of a wave. If you send light through a dielectric media at a frequency where it resonates with the wave, you go into anomalous dispersion. It's very dissipative. And finally, when it's 0, then the group velocity equals the phase velocity. I'll show you a graph in a minute for why that's usually referred to as linear dispersion. I prefer to call it dispersionless. It's the case for light and vacuum, where the group velocity and phase velocity are equal. In that case, omega and k are linear with each other. And that's where the term linear dispersion originates. So those are 3 different dispersion regimes. I want to look now at 3 very special cases, not following the regime argument, but in this case, when dv phase by d omega is specifically greater than v phase divided by omega, that is, it's greater than k. I have the expression up here that relates to them. When that's the case, the denominator becomes negative. That is, when dv phase by d omega is greater than 1 over k, the denominator becomes negative. Group velocity becomes negative. The group velocity and the wave vector for the wave are in opposite directions. That's the case for left-handed media, that is metamaterials, which is a hot research topic in applied electromagnetism these days. When the phase velocity is linearly proportional to omega, then dv phase by d omega is just v phase over omega, that is equal to 1 over k. V phase divided by omega is 1 over k. The group velocity goes to infinity. That's a special case called extreme anomalous dispersion, which arises in the physics of plasma. Another important case is when this derivative blows up. dv phase by d omega goes to plus or minus infinity. Because when that happens, the group velocity goes to 0. The wave stalls out. You've got a wave packet where the phase velocity continues, so the phase oscillations continue to propagate, but the group is stalled out. To see a case where that might happen, let's evaluate that derivative. So d by d omega of v phase, which is omega over k, use the product rule, 1 over k minus omega over k squared dk by d omega. So that goes to infinity. Now when I look at this, what is going to infinity? K is not going to 0, so it's not that. And omega is not going to infinity, so it's not that. It must specifically be the derivative dk by d omega that's blowing up. Or rather, d omega by dk is going to 0. Omega has become insensitive to the wave number k. You have an entire range of wave numbers where omega doesn't change. Or rather, an entire range of wave numbers where energy doesn't change. So one value of omega, which is energy over h bar, corresponds to a range of wavelengths. We will be confronted with this phenomenon later in this course when we get to propagation in a periodic potential. When that happens, you have normal dispersion most of the time. Then it starts to curve off and get to this point where d omega by dk goes to 0, as you have a range of wave numbers that accommodate one frequency. And then you get a jump, and then you have that same derivative going to 0, but from the opposite sign, so now it's taking off. You return to this previous type of dispersion. That's the case of an electron propagating in a crystal or in any kind of periodic potential. I've given you a basic introduction to dispersion. Different dispersion regimes based on whether the group velocity is faster or slower than the phase velocity. In these special cases, one from applied electromagnetism with metamaterials, one in plasma physics with extreme anomalous dispersion, and one from quantum mechanics with propagation in a periodic potential giving extreme normal dispersion.